Welcome everybody to the fourth Survey Cadence Optimization Workshop. My name is Federica Bianco. I chair this committee and I am Deputy Project Scientist for LSST Construction. Today you will hear from me, from Lynn Johnson, Peter Joachim from the Survey Strategy team, and I want to acknowledge all of the members of the SCOC in the preparation of these slides. You can find the link to the slides in the Slack channel for this meeting, as well as in the Google Doc that I shared on the Slack channel where we can take notes collaboratively. If you joined early, you saw this slide, which reminds you that we have a code of conduct for the meeting. Of course, harassment in any form is not allowed and not permitted. We have an OMSBOT person for the meeting, that is Steve Reitz, project scientist for construction, and you have his email on this slide as well as in the workshop webpage. I do not see the chat because I'm sharing my slides. So I'm going to ask SCOC members if you see anything that needs to be taken care of on the chat or on the Slack channel, please let me know, and I will interrupt me at any point. The code of conduct can be reviewed on the workshop webpage, and there's a QR code for this here if you forgot the content of it. But at a very high level, Rubin Observatory adheres to the principle of kindness, trust, respect, diversity, and inclusiveness at all times via any activities of the organization, including this workshop. The agenda of the workshop is as follows. This workshop will take place today, as well as on Friday, both days from 9 to 12 Pacific time. We are in the first session from 9 to 9:30, where I will introduce you to the workshop and to the SCOC in general, and briefly recap the recent activities of the SCOC, or Survey Cadence Optimization Committee. Lynn and Peter will talk about updates to the OPSIM, the simulation software that provides the simulations of the survey strategy. And then we will hear presentations from task forces, and we will talk about some key differences in the most recent simulations of the survey strategy due to updates to the software and to the parameters of the system as we come to know them approaching operations. That will happen in session 3 from 11:15 to 12. On Friday, we will hear more presentation from task forces, and we will talk about year 1, early science, but in particular, we will talk about the process of creating templates in year 1 that will enable alerts. And the last session from 10:45 to 12 is an entirely community-focused session where we would love to hear from you, the community, and the science collaborations, your thoughts, impressions, and concerns. If you are in a science collaborations, the liaisons into the science collaborations have reached out to the science collaboration to organize this session. I'll have a slide later that shows the straw person plan for the session, but there's still time to add contributions and indicate that you want to contribute. The Survey Cadence Optimization Committee, or SCOC, is formed by, at the moment, I think 12 members. I want to thank them and acknowledge them, and I want to read out their name explicitly: Timo Nguita, Franz Bauer, Louise Edwards, Rob Jha, Rachel Mandelbaum, Adam Miller, Knut Olsen, Colin Slater, Stephen Smart, Jay Strader, Rachel Street, Kat Volk, and Lynn Johnson, myself. We are ex officio, so non-voting members on the committee. The SCOC is also supported by the survey strategy team, which at the moment includes Lynn Jones, Peter Joachim, and Eric Nielsen. And they provide the simulations and run the metrics that evaluate the success of a survey strategy on specific science cases, as well as help us interpret them and understand them. The SCOC works, generally speaking, as follows. We meet at least once a month. We have liaison into each science collaboration. Those people are indicated in the previous slide, and their job is to establish and maintain bilateral communication with the science collaborations so that the community that is involved in a science collaboration, which is the largest fraction of the scientific community that is actively interested in working in Rubin, is aware of our activities and can contribute and communicate with us at any point in time. We also hold monthly office hours. At the moment, these are set for 7 a.m. Pacific and the last Monday of the month. These may change as the semester goes on, and we update our schedule with new academic commitment, so keep an eye for announcements of possible changes of this time slot. But we do hold office hours every month. The SCOC also shares and receives updates on the community forum. This is community.lsst.org. If you're not familiar with it, it's a forum. Think about something along the lines, of Stack Overflow, where we post updates. We also receive and answer questions. We have monthly monthly meeting minutes that are available, shared as well on this forum. And of course, we have annual workshops, and you are here for one of those events. The Survey Strategy Optimization Committee has worked, and in general, the optimization of the survey strategy for LSST is a heavily interactive and continuous process. It started roughly in 2014, or started formally in 2014 with the creation of the math software that enables the scientific community to produce metrics that evaluate the success of the survey strategy on specific science cases. That goes along with simulations of the survey strategy that are produced with the OPSIM Operations Simulator. And in this sort of timeline that goes from 2014 through 2023, you kind of see the main phases of this process. And you see how really, truly iterative it is. Every time you see an icon that shows people, that is a community contribution, an official point in time where the community was able to convene or share their impressions, their thoughts, their desire for the observing strategy with Rubin and with the survey strategy team and Rubin at large. You also see the number of simulations growing significantly. We started with 14 simulations when the first point of interaction with the community was established. This was the creation of a live document that we now call the COSEP in 2015, led by Phil Marshall. And then we produced more simulation. We had white papers, 46 of them from the community. We established the SCOC to better interact with the community, solicit contributions, and evaluate, review this contribution, and design the survey strategy accordingly. That was in 2019. We had more simulation, version 1.7. You'll see this a few times in the slides today. We had more community contributions, the Cadence notes of 2021, 39 white papers. Throughout, we produced reports of where we thought the survey strategy was at that point, how we thought it should be conducted at that moment. And as you see, these reports, there's been more than one report. There's been a report from the SAC, a phase 1 report from the SCOC, a phase 2 report released in December of last year by the SCOC, and we expect one to come out this year. As a result of this, the survey strategy of LSST has changed profoundly and has improved profoundly. You will see these slides in more detail when Lynn talks about the new updates to the survey strategy, but just see how the footprint of the survey has changed over time. This is precisely in response to comments and feedback from the community that allowed us to create a survey strategy that better responds to scientific priorities. And you will see plots like this that show how a specific metric for science responds to the survey strategy as we have it today, or as we design it, or we hypothetically consider changes to it. In these plots, you see every row is a science case as measured with a metric, a math. Lynn will talk a little bit more about this. And the color goes from red to blue, indicating worse to better, compared to a specific simulation. In this case, the version 2.0 simulation is the point of comparison. And generally, you see how over time, so from left to right, as simulations changed in response to feedback from the community and actions of the SCOC, the plot is populated by more blue, which is an indication of success, an indication that we can achieve more science goals and do better on specific science goals. Of course, this is just a subset of the hundreds of science metrics that the SCOC evaluates in this optimization process. And of course, you see that they can't all go towards bluer color. They can't all be simultaneously optimized to be best. This is a compromise. There are compromises that have to be made to find the survey strategy that produces the overall highest scientific throughput for the entire scientific community. And this is the job that the SCOC is committed to. I also want to point out that your contributions, the white papers, the Cadence note, and additional contributions that you have shared with the SCOC, reports that were unsolicited or solicited in more specific forms, have a venue in the scientific literature. We work with the AAS journals and with the editor Chris Linton to set up a focus issue on Rubin survey strategy that accepts submissions of papers dedicated to this work. The reason for doing so is because we wanted to make sure that the scientific community that is working with Rubin to help us develop the best survey strategy for LSST can get traditional academic rewards for their work, and this doesn't interfere with their academic success, but rather enhances it. So we set up this focus issue, which is dedicated to survey strategy. That means the editors are aware that typically the papers in this issue will not contain scientific discoveries and will be rather technical, things that may generally raise red flags from editors and reviewers. And with the science issue, we facilitate the process of publishing papers of this nature. And there are currently 20 published papers on this focus issue. And I want to encourage anybody that has done work on survey strategy and hasn't done so yet to consider submitting a revised version of their white paper or Cadence note to this focus issue, which is still accepting submission and will continue to accept them until we expect the end of this year. The focus issue will close with the paper that describes the recommendation for the initial version of the LSST, which we expect will come out early. Will come out as a recommendation at the end of this year and as a paper early in 2025. Let me tell you a little bit about the timeline for the current phase of the work of the SCOC, which is phase 3. Picking it up from the last time we got together as a SCOC community workshop or a SCOC science collaboration workshop, which was in November of 2022. After that, we released the phase 2 recommendation. This document is called PSTN 055. You received an email yesterday with links to this document. It's also posted on the website of the workshop, and perhaps one of my colleagues can post it on the Slack right now. This describes how we thought, as of the beginning of this year, the survey should be conducted. The SCOC at that point had a rotation, and I want to acknowledge and thank the former members of the SCOC. About a half of the SCOC rotated off. The work of the SCOC since then has largely been organized in task forces, which do targeted work on specific questions that were left open in the phase 2 report. I'll get back to that in a minute. We also solicited additional feedback from the community, updates on their thoughts about the observing strategy in the form of a Google form. We received 14 responses from that. I think I marked that in the slide, yes. And we met at the PCW 2023 with the community. We discussed the task forces, solicited participation into the task forces, and today we are here to meet again with the community. A couple of things that are not on this timeline but are worth noticing. More simulations have been released since the phase 2 report and the associated simulations. Those were released in December of 2022. And in November of this year, we released new simulations, which Lynn will describe in some detail after this talk. Looking ahead, I want to point you to another workshop, which might be of interest. This will happen in March. 18 through 21 at Berkeley and online in fully hybrid mode. This workshop is dedicated to talking about target of opportunity strategies for LSST. We will meet again with the community at the 2024 Rubin Community Workshop, which will be in July. We plan on reporting on our plan for the phase 3 recommendation at that point. And in late September, we plan to release our phase 3 survey strategy recommendation. This report will represent a recommendation for how we should start the LSST. We expect that recommendation will be followed through year 1. Of course, at that point, we won't have finished commissioning, so we will need to await the commissioning results. Those may lead to revision of the survey strategy. Of course, we don't expect substantial revisions, but we will respond to commissioning and review the survey strategy at that point. And in fact, the survey strategy of LSST will continue to be revised, leading to and during LSST. We will present the report at the Rubin Community Workshop. We aim to make a draft public before September 1st, so that we can get feedback from the community before the final release. And community input is always welcome, of course, in a number of ways. So in fact, what are the ways in which you can talk to the SCOC? Your first point of contact, if you are in a science collaboration, is your science collaboration liaison. As I mentioned in the initial slide, where I presented the SCOC members, it's indicated which SCOC member is a liaison into your science collaboration. This information is also available on the SCOC website. We also have office hours, as I mentioned, and we post updates and receive questions on community.lsst.org. I wanted to give you a sense of how this forum works if you are not familiar. We have topics, so you see here the topics: science, survey strategy. All survey strategy discussion are under the topic survey strategy, which is where you land if you click on the link on these slides. And you can see different topics, including some posts by the SCOC and some posts by the community asking questions about simulations and survey strategy. Here is an example of how one of those posts can look. I mentioned that the SCOC will continue to work in operations, and the survey strategy will continue to be reviewed throughout LSST. Some reasons for this are obvious. There will be changes in the scientific landscape as LSST produces transformational science, and we need to respond to those. We expect, for example, to need to respond to modifications of the target of opportunity strategy, to new scientific priorities, and to unexpected events in operations. The SCOC will expect to recognize and address these changes, and in a couple of ways. Of course, this is something that we are trying to envision as how would this process look in operations? This is subject to change as the reality of operation settles in, and we realize that there may be better ways to do this. But at the moment, the plan is that the SCOC will continue to have liaisons into the science collaborations. We'll have an annual call for feedback as well as an open portal to share feedback on an ongoing basis. We're committing to reviewing the survey strategy annually, but we may review the feedback more readily and be able to respond more readily if needed. And we will release quarterly and annual reports on the survey progress. I want to spend a couple of minutes telling you specifically about some activities of the SCOC since the beginning of the year until now, and for the rest of the year, the beginning of 2023, that is, that respond specifically of questions left open in the last survey strategy recommendation, PSTN 055. On section 4 of PSTN 055, we explicitly wrote a compendium of points that were open for further exploration and refinement. I'm going to go over all of them one by one for a couple of minutes and tell you how we are addressing them, beginning with the one that we have already addressed. At the time, we were investigating which filter should be swapped on the filter wheel. Now, the filter wheel of LSST hosts 5 filters, but the survey is conducted in 6 filters. So one filter has to rotate in and out. We do that following lunation. So we rotate between a very blue band and a very red band, depending on the phase of the moon. We have considered and simulated many schemes for swapping the filters, and we have landed to swapping U and Y out of the filter wheel on a roughly monthly basis following lunation. And this has significant advantages for supernova science, as well as no scientific losses for any other metric. So this question is now closed. Another open question is the uniformity of the coads of LSST in the presence of a rolling strategy. Now, in phase 2 report, we recommended that LSST is conducted with a rolling scheme, which means different areas of the sky are prioritized within the year to get a slightly denser cadence and then deprioritized to prioritize the rest of the sky in the remaining part of the year. This provides full sky coverage, but also a slightly denser cadence that helps time domain science in the on region of the sky. The recommendation is to run a 0.9 rolling weight. This just is the intensity of the rolling. This number should be not considered literally, and on a half sky region. However, we know that this has an impact on the uniformity of the static data releases, and that impact may affect cosmology and other sciences. We initiated a task force to identify the impact of rolling on the coads, to identify the requirements in uniformity, and to see if survey strategy tweaking can help address the concern of the scientific communities that would like to see uniform coads. You will hear from this task force by its chairs and members of the task force later today. Rachel Mandelbaum is chairing the task force. The next topic is the Milky Way. We had not finalized at the time of phase 2 report the survey strategy for the galactic plane and Milky Way area, neither in filter balance nor in footprint, although we had made a lot of progress in defining the footprint, nor in what the rolling scheme should be on the galactic plane. We have a task force active on this topic, and you will hear from them tomorrow. You will hear from the chairs, Jay Strader and Rachel Street. A third task force is just being initiated now, and Surabja will talk about it today. We'll present it and again solicit interest today. This will define the intranight cadence for deep drilling fields. An additional point was that the SCOC had recommended a filter balance, essentially the filter balance that we had in the survey strategy simulation, starting with baseline 2, recommended that it shouldn't be changed, but acknowledged that if there were changes in the understood throughput of the system, then maybe tweaking the filter balance should be considered. We do have changes in the throughput system. You will hear about them today. And we are working on identifying whether tweaks in the filter balance and tweaks in the strategy can give even more scientific throughput to the survey than we had with the version 3 with the phase 2 recommendation. This is an opportunity to get even better science out of the system. An additional point was the decision about the details of the target of opportunity strategy. That can mean what kind of targets to respond to, how to algorithmically pick them up, what is the human involvement in the process, and what is the sequence of observation for each target of opportunity. The TO program has been recommended by the SCOC in the phase 2 report to use up to 3% of the time with the scientific motivation of follow-up of gravitational waves, but with the possibility of expanding it to other exciting and critical science cases in the future. The workshop that we will hold in March, which is open to the community, it has no conference fee, and we're working really hard to provide travel support for participants, but is also available online, so travel expenses should not be a bottleneck. Will get the community together to define a recommendation for how to conduct the TO program. This recommendation will be revised and reviewed by the SCOC and incorporated in our phase 3 report. And I want to thank Igor Andreoni, Tim Lister, Raffaella Margutti, Graham Smith for being on the SOC of this meeting. Here you have the link, the email that you can use to contact us at this meeting, as well as the website of the meeting. In the phase 2 report, we indicated we were waiting for commissioning to assess the viability of switching the image taking scheme from 2 15-second exposures to snaps to a single 30-second exposure, and that after this viability assessment, we would decide whether scientifically that was which was the best plan scientifically. At the PCW, we heard the community indicating that they thought it would be a good idea if we had the decision about the scientific merit of the 2 survey strategies ahead of time. And we heard you and we agree. And so this is a discussion that is on deck for the SCOC in April, March. We already have collected feedback from the community in a number of occasions about why 1 times 30 seconds versus 2 times 15 seconds should be preferred for individual science cases. We will review it and assess what is the best scientific way forward. And this is the last point. We recommended that the SCOC works closely with the early science team to define the observing strategy in year 1. We will hear about Eric Belm tomorrow about the construction of templates, and we are working in coordination with the early science Rubin team to define the year 1 observations. This is the last slide. I want to remind you that we have community contribution session tomorrow, 10:45 to 12. Contact your SCOC liaison and SC representatives if you want to include some input and you haven't had the chance to indicate that yet. If you're not in a science collaboration, we also want to hear from you. So please contact me directly or indicate so in the Slack channel. And I want to ask the SC representatives that will give the science collaboration presentations to review this straw person plan and tell me if the schedule works for them. And if you're in a science collaboration that does not intend to present, but you see yourself in this list, don't worry. I put all the science collaborations here just to make sure that we wouldn't run out of time slots. But it's okay if you don't feel like you have anything that you want to share tomorrow, but you will be welcome to do so if you wish. And with that, this was the intro to the workshop and the work of the SCOC. We are already 2 minutes late. So if there are Friday, not tomorrow, thank you very much. Thank you, Adam. If there are any questions, maybe one question if it's urgent, otherwise I will let Lynn go to the next session. I don't hear anything and I don't see anything on the chat. Meg.
I've been lengthy chat with Lynn about this, and I want to raise this. I'm concerned about the timeline, in that end of September is right when people have to, let's call end of September really early October, right? Same metric. Some people have to write NSF proposals a month before for their finance offices to process them. And this is the year to write NSF proposals to fund your several years of science, beginning science with LSST. Not having enough time to adjust the cadence, effectively, some people have 2 weeks, right? Maybe not enough for the full community to understand and process and write it in their proposals, and not having the say it's finalized because your report's not out may hurt us if people don't understand what it means and thinks the cadence may dramatically change. As people are aware, there have been issues in some of the funding and people understanding the status of LSST. And so I ask, or rather a consideration from the SEOC of, does it really, if you shifted your schedule by a couple months, is that really going to change your work? But you would, in the grand scheme of things, that it would change the cadence significantly and the decision that will be made. If it doesn't, it would allow the community, if we got it at the end of July, right, the baseline strategy, it gives us time to digest it, write the papers we can put in the focus issue that analyze that for the last stretch of this is what the cadence looks like, and gives people time to understand what that means in terms of their predictions so that they can write the best NSF proposals. And so I would ask the SCOC to consider maybe shifting their timeline by 2 months to end of July, just to raise that issue, since maybe you weren't thinking about NSF proposals and that much of the US community will be doing that. And some people need a month early to submit their proposals from other interactions in the source of science collaborations. We found less than a month gives problems for some people. So I just wanted to raise that issue since you hadn't talked about proposals. That's just because there's been a lengthy discussion of that on.
Thank you, Meg. This is an excellent point. There is not enough time. Let me just be very explicit. There is definitely not enough time for the SCOC to finish a report by July. So that's like, we have a detailed timeline that we are coming up with to finalize all of these decisions. Everyone takes time. Every one of those decisions takes time, takes simulations, and there's just not enough time to finalize them all. However, what I want to say is that as we come up with, as we narrow down the options, or we come up with a resolution of any of the outstanding 9 points on that we're left open in phase 2 report, we intend to communicate that explicitly and clearly in as many ways as we can. We intend to discuss that on community, to have the science collaboration talk about that, the liaisons into the science collaborations talk about that, to the science collaborations, and we intend to release a draft of the report ahead of time, as well as present the content of the report at the PCW, at the PCW, which will be at the end of July. So we're not going to be able to release the report earlier. But we will be transparent and open about the content of the report at all these points in time, so that the community can know where the survey strategy is heading and what details still need to be refined. I also want to say that largely the survey strategy has been defined to a very significant level of detail. And these 9 points that are left are really not, for the most part, significant enough that it would determine a critical change that I would expect a lot of people would be impacted by in the writing of a proposal. The way in which we will conduct year 1 observations is a really important point if you want to write a proposal that is based on year 1 science. That unfortunately necessarily will be the last thing that we know, just because that depends so critically on a lot of things that will happen in commissioning and science verification. I don't see any other hands raised, and 7 minutes late. Lena, I want to pass the microphone to you.
Okay, let's get that shared. Okay, well, luckily, I think the things that I'm going to talk about are first of all, things you might already be super familiar with, and secondly, let's get some of these buttons out of the way a little bit more. Okay, so I'm supposed to talk about the survey strategy, our simulations, and so on. I just, as Fed mentioned, over the last 5 years, we've had a lot of changes, and they are, in large part due to all of these contributions from the science community. The changes to the footprint, the changes in the cadence on short timescales, all of these, they've improved the science metrics, and they're all coming from all the contributions from the community that have gone to the SCOC and then through the SCOC phase 1 and phase 2 recommendations. So I wanted to also say thank you for all of your hard work, for all of those, all of that input and all of that evaluation. At the moment, we're at baseline V3.3 of the survey strategy. And there we go. You are all probably super familiar with this, so I'm just going to go through it relatively quickly. But as a reminder, especially if we picked up anybody new, we have these sort of different modes, parts of the survey. There's the main survey, YFAST Deep. There's mini surveys, which are surveys, parts of the survey which cover relatively large area, but maybe only take 3 to 10% of the survey time. And then there's micro surveys, which are like 1 to 3% of the total survey time. And then there's the deep drilling fields, which are a little bit of a kind of different thing. But there's like single pointings that go at least 1 magnitude deeper than the YFAST Deep co-added depths. And currently those are taking about 7% of the total survey time. You can find the current baseline survey strategy at the link here, which I realized you guys didn't actually get a link to the slides, so I will put these links in Slack when we're done here. We haven't really shown these footprints like quite like this before, so I thought it would be useful to just point out, like, this is in this plot on the right here, we have the low dust YFAST Deep, that's the yellow area. And then we also have areas of YFAST Deep level coverage. So these are parts of the sky which get about the same number of visits per pointing, about 800. But their filter balance is likely going to be different than the low dust YFAST Deep because they're sort of focused on different science goals. They're in high dust extinction areas. They're more interested in looking at stars in these parts of the sky. And so the filter balance is likely different. The low dust YFAST Deep uses a rolling cadence, and we're currently thinking about, like, how do we extend that rolling cadence to other parts of the sky, or should we? And in the first year, there is no rolling, and that lets us get uniform YFAST Deep coverage for catalog creation, photometric calibration. The typical cadence of coverage in the YFAST Deep, kind of, useful back of the envelope kind of numbers. Most of the visits are acquired in pairs, separated by about 33 minutes. The pairs are in different filters. So currently we pair U with G, U and R, G and R, R and I and Z, Z and Y, and then Y and Y. And about 3% of those pairs also get a later triplet visit 3 to 7 hours later in one of the same filters of the pair. In general, we return again to the same pointing 2 to 4 nights later, not necessarily in the same filter. When we return depends a bit on whether it's an active rolling season or an inactive rolling season, because that will flip up and down. And as Fed mentioned earlier, we load Y band. So U and Y load in and out of the camera every 2 weeks or so as we cycle between bright time and dark time. The mini surveys you can see here. So we have the North Ecliptic Spur mini survey, the Dusty Plain, and the South Celestial Pole. Sorry, that should be South Celestial Pole. And these are areas which get on the order of a few hundred visits per pointing, and these filter balances are quite different than the YFAST Deep area. Note that the NES does not get U or Y band visits because those just aren't useful for solar system objects. And then the deep drilling fields. So we have 5 deep drilling fields. They use between 6 and 7% of the overall survey time. As of phase 3, the V3, sorry, the phase 2 recommendations, the Cosmos field, that's this one that's over here, sort of more by itself. And that field gets an accelerated coverage, so it gets to full tenure depth, about 20,000 visits by the end of year 3. And then it continues to get covered at the normal rate for deep drilling fields. But the idea is that by having that early completion of the Cosmos field, we get to understand what the other deep drilling fields will look like after 10 years. We understand just a lot more about how that processing is going to be able to be accomplished. The other special field is the Euclid Deep Field South. So that's been adopted as the 5th deep drilling field. There's been announcements about that. But it is actually 2 separate pointings because it's a bigger area. And so it doesn't get twice the coverage, still has about 20,000 visits, and they share these between the 2 pointings. So the cadence for these deep drilling fields is still under development. And this is one of this is the part of the job of the Deep Drilling Task Force. And then microsurveys. You can think of this as a few percent extra. So as of the phase 2 recommendations, the SCOC recommended adding the near sun twilight microsurvey with the potential addition of a northern stripe microsurvey if time allows. Additional microsurveys will be considered after the start of operations as survey efficiency is better understood. So there will be, I think the SOC plan is to have a call for microsurvey proposals in the first year of operations. And then also target of opportunity observations. I put these in here. They are on the level of a microsurvey, but those are also a little bit special. The near sun twilight microsurvey covers basically the ecliptic plane at low solar elongation, which translates to high air mass, and this enables discovery of inner solar system objects. This is taking about 1.5% of the total survey time in the current simulations, and it's very focused in twilight time. Okay, so specific updates for V3.3 as we come out of V3.2. The survey strategy was mostly the same. There was a bug fix because we found that in U-band, at the end of year 1, we were kind of essentially pausing the U-band observations. And this is just due to sort of an interaction between some competing basis functions in the scheduler and plus some various other things. So we just basically fixed that problem, and now U-band just continues getting observations at a consistent rate over the entire survey, which means that we got a few more observations in U-band per pointing in V3.3 than we did in V3.2. And it's only a few, it's about 7 visits per pointing. So this is about sort of a boost about 15% if you look at it in that way. And you can see here's a plot like going from baseline V1, this is probably 1.5 or 1.7, through V2, 2.1, 3 to 3.3. These are all the baseline simulations, and those are the median visits in U-band in the wide fast deep. And so you can see they increased a little bit, and in the other filters they maybe decreased slightly. We also had a slight change to the parameters in the simulation that reduced the number of back-to-back filter changes that we had. So we had a few cases where we were taking an observation, changing the filter, taking the same an observation in the same field again, or in a different place, and then changing the filter again. Mostly this was sort of just due to a rapid turnover of observing modes during twilight. So this isn't a large change on the actual survey strategy. It's was probably the equivalent of about 750 visits in observing time. But it's just a slight change that we implemented. The biggest change that happened in 3.3 compared to 3.2 is that we used an update to the system throughput curves. So all the way up to 3.2, we've been using the same set of system throughput curves. And as we've been going along, the telescope and site and the camera team have been making measurements of things like the camera reflectivity. They've recently had actual measurements of the filter throughput curves, things like this. So in 3.3, we've switched over to their best guesses of as measured throughput curves. And so this does make a difference in what the throughput is. The other change, we'll talk about this more in session 3, is that we've changed from having mirror coatings that were aluminum, silver, aluminum to all silver. And that does put a higher throughput into GR-IZY bands, lower throughput in U band. And like I said, we'll talk about this more in session 3, but this is the biggest change that happened in 3.3. And we'll talk about the impact.
I have a first question. I don't know if I can ask it now or if I should wait.
I don't have very many more slides to go through.
Okay.
If you want to wait, and then we'll come back to this. So the other thing we have started doing as of a few simulations ago, maybe V3, is to run variations on the cloud coverage. So we have this big cloud historical database, and by offsetting into different years, we can essentially sample slightly different weather. This gives us a way to get a weather estimate on what the error for a particular metric would be. So what you see over here in this plot is just the total number of visits in a simulation for each of these different weather runs. And so the points are the actual number of visits for each of these weather runs. The blue line in this error bar represents what the standard deviation of that weather estimate was, and the red line is sort of the full minimum to maximum variation. So we've been starting to adopt these values, the standard deviation in particular, as an estimate of what kind of variation you might expect due to weather when we report metric results. So that's one thing that we've started doing, and you may have seen some of this metric plots like this. When we're comparing different runs, there is some intrinsic weather variation that will happen, and this is our way of getting some kind of estimate for that. The other simulations we have in V3.3, we have a set of rolling cadence simulations, we have a set of Milky Way galactic plane coverage simulations, and a set of some variations on DDF coverage. And these are all in support of the various task forces. We do have some other internal runs that were created by SEOC requests, but those are still sort of internal investigations. These are sort of some of the ones that we actually have available for people to look at for task forces. And oh yes, I did want to point out after we made V3.3 simulations, this was all done with the Rubin Sim software, but we have had now a split in our software because we want to be able to have the scheduler software more separate from all of our metric software. The metric software has a bigger dependency chain, like people contribute metrics that need, let's say George, or more complicated Python packages. And in order to keep the dependencies down for the operation of the scheduler at the summit, we pulled the scheduler code out of Rubin Sim. And so now it's in its own software package called Rubin Scheduler. Rubin Sim now has math, and you can still Conda and PyPI install both of these. And note Rubin Sim depends on Rubin Scheduler. Things should be about the same. There were very, very minor code changes, but this is like as of 3.4, simulations will be produced using Rubin Scheduler and then analyzed using Rubin Sim. And that is all I wanted to say for this session. So I think I've got us back 8 minutes.
You made up for my extra time. Thank you very much. Let's see if there's a couple of questions. Some of them were answered in the chat. Simona, do you still want to ask your question? Do you want to wait for the next session?
I will wait for the next section. Thank you very much.
Yes, in the next session, we'll talk in detail about this change of throughput, the motivation, as well as the impact on the survey overall and for specific scientific cases. Are there any other questions? We are 7 minutes early to the next session. So I don't want to start the next session ahead of time just in case anybody had planned to join specifically for that. So Rachel Mandelbaum, since you will be in the next session, is that okay if we wait until the top of the hour to start? If there are questions, please go on and ask. Eric, thank you for the reminder. Yes, substantive questions on Slack are better than on the chat. I will save the chat, however, and repost it on the notes and probably make a link to the Slack as well. Yes, there is a link to the slide in the slide deck. Let me reshare the link. So if you go to Slack, you do see all the links. The slide decks are posted as a bookmark on that channel, as well as, let me just get to the correct Slack channel, as well as you can find a link to a live notepad. It's at the beginning of the Slack, so right now you're gonna have to scroll up for that. The slides are included in this link, which is the link to the live notes. I think that's probably the best way to do that. That should be a one-stop shop if you want to add. And by all means, the community who's preparing slides for Friday, if you want to add the slides to that deck whenever you feel comfortable, that would be outstanding. So we can have them and see them additionally to your presentation. If there are no questions, maybe in the next 5 minutes, just I encourage you to stretch your legs and get a glass of water. But whoever wants to stay here, if you get brave and decide to ask a question, at least I will be here. In minus 2 minutes, please make your way back to your laptop or computer. Maybe let me take a second to once again thank and recognize the members of the SCOC. Could you raise your hand, your digital hand, if you are on the SCOC and on this call so that the rest of the community sees you and knows who to talk to if they want to. Thank you very much. And there's a few other members that will join at different points in time during the workshop. I see you, Luis, thank you. All right. That brings us to just about the right time to do a check that Rachel can share the slides or can share the screen. Excellent. So the next session is reports and discussion from the task forces, specifically the uniformity of COADs and the deep drilling fields task force with Rachel Mandelbaum and Saurabh Jha. And after that, there will be a break. So take it away.
Okay, thanks, Fed. You're going to hear now an interim report from the SCOC Uniformity Task Force, of which I'm the chair. And we're going to have task force members who are presenting their own work for the most part. I'm just going to give a little preamble to set the stage so people understand what is this task force and what are we trying to accomplish. So this is just me re-showing a slide from Fed's presentation about one of the open questions in the previous SCOC report. As she mentioned, the recommendation was to implement a rolling cadence, meaning an observing strategy that at certain times emphasizes some parts of the sky over others and has a more frequent observing schedule in those emphasized regions. But rolling impacts the uniformity of the data releases, which can be an issue for certain non-time domain science cases. And so without reading this in detail, the main point was that, that needs additional investigation and metrics to quantify that effect and potentially explorations of alternatives, alternative rolling strategies. So since I realize there's a very broad scientific audience here, I just wanted to, kind of give one slide of what do we mean by uniformity? Like, what is that, and why do we care? So for context, static science cases will typically start with the object catalogs derived from co-added images at a given data release. So Rubin Data Management will, process the individual exposures, co-add them, and then produce an object catalog that has measurements for the detected objects based on that coad. So if the coad has spatial variations in, for example, the depth or the PSF size or other quantities, that will affect the survey completeness, the detection rate for the stars and galaxies as a function of position, and also, their measured properties. And so that will affect the samples that you select from the coad in potentially complex ways that are spatially correlated. So just to give kind of a visual representation of this, this is a map that I produced by taking the baseline version 3.3 observing strategy. And this is a map essentially of the I-band co-added depth 3 years into the survey. So when a rolling cycle is not fully complete. And so the color scale indicates the depth. The brighter colors are deeper, that's the yellow, and the green is shallower. And you can see that the striping due to the rolling is, quite visually evident, and would also be evident if you tried to select catalogs using the coad. They would be quite non-uniform with these large scale spatial patterns. So we're especially concerned about excess difficult to model fluctuations that can pose a challenge for analysis. So no survey is ever going to be perfectly uniform. That's just not achievable. But the question is, what's the impact of the additional structure due to rolling compared to what would be achievable otherwise? So, the issue became particularly urgent once a rolling cadence was incorporated into the baseline observing strategy. And so the SOC established a task force that would provide opportunities for members of any interested science collaboration to offer quantitative input. And this task force activities include generating quantifiable science-driven metrics for uniformity, enabling an understanding of required, desirable, and sufficient uniformity per data release, and exploring improvements to the rolling strategy that would maximize the uniformity while remaining within, the recommendations of this, rolling cadence with half sky rolling and a 0.9 rolling weight. So the initial members of this task force are listed here. It includes a few SCOC members, and then the SCOC liaisons to different science collaborations asked if other individuals were interested in participating. And it also crucially includes Peter from the observing strategy team for this exploration of, alternative rolling strategies. A lot of the recent activity has been within DESK, and that has resulted in new contributors to this effort beyond the specific individuals who are listed on this slide. And you'll hear from some of those new contributors in the talk right after mine. And I want to emphasize that, others are certainly welcome to engage. We're very happy to have individuals who are interested in putting some thought and effort into this very important question. But there has been significant progress in the past 4 months. That work is still ongoing. So the task force is not ready to present conclusions, but task force members have volunteered to provide an interim report on their ongoing activities that gives you a sense of the flavor of, all of these different kinds of activities that are now happening. And so with that, I do want to pause and take any questions on this context. But after this, we're going to switch to an update from task force participants on their ongoing work. So let me just pause for questions. Fed, did you want to say what you posted in the chat, or was that?
No, it's just I'm just trying to clear some taxonomy for people that might be newer. You were showing the baseline, that's the incarnation of our recommendation. You may see survey strategy that have different names that don't include baseline. Those mean like variations of our recommendation that that specifically investigate some parameters, but nothing crucial and nothing specific to your talk.
Yeah, but that is good that you brought that up, because you'll see that in the plots provided by some of the task force participants momentarily. You'll see a number of variations on baseline. You'll also see something called no roll, and that's something which is not consistent with, the rolling cadence recommendations. It's what would happen if you did the baseline strategy without rolling, just to provide, kind of an upper limit on uniformity. It's, it's a useful test case, even though it's not, consistent with the SCOC recommendations. So from there, I'm going to stop my screen share and hand it over to Erica Weiser, who's going to lead that presentation.
Okay, hopefully that was a seamless switch. Can everyone see the presentation?
Yes, we see the entire browser though, with the
Yeah, and it's cut off on the right.
yeah.
Ah,
Oh, now it's, well, it's a little bit better.
Now we see the browser with the URL space, but
I can do it the other way. Hold on a second. Actually, I think it's going to have to be that way.
I think that way was fine.
Thanks.
As long as it's zoomed out enough that we see the full slide. That's good.
Great. So we wanted to give this update on uniformity issues, and the group that's listed here can be best thought of as the intersection in this Venn diagram that we might all love and know between the Uniformity Task Force of the SCOC and the Dark Energy Science Collaboration, people drawn from the Survey Coordination Working Group of DESC. The motivation, building on what we've already heard today, is that the version 3.3 strategy includes many enhancements and a rolling procedure that's working very well. This is very good for a whole wide range of science, including many different DESC science metrics, particularly for transients such as 1A supernovae. We're still testing the impact of the rolling cadence procedure on static science cases, weak lensing shear, galaxy clustering, or clusters of galaxies. And what we really care about are what it looks like at the time of relevant data releases. And so to explore that, we've built math metrics that go from observables like the limiting magnitude, basically the depth over the whole survey area, to our science metrics. And that's a work in progress. We'll show you what we've achieved so far. Just to give you a sense, DESC does not plan to do a cosmological parameter analysis at every annual data release from LSST. It'll take us more than a year in all likelihood to do the analysis, so we think we'll do this at something like years 1, 4, 7, and 10. And so that's where we're really looking for the survey to achieve something uniform enough to get our science done. The goals of this subgroup's work are to provide the SCOC, as part of its uniformity task force, with improved science-driven metrics for survey homogeneity, as well as to help interpret those metrics, and also to suggest variations in rolling when we come up with ideas that could improve the homogeneity for selected data releases at those key intervals, like year 1, 4, 7, 10, while maintaining the benefits for transient science. We'll show you today a few parallel efforts. We're trying to develop metrics that quantify the impact of non-uniformity on these three areas: photometric calibration errors, the spatial variations in the mean redshift of galaxies put into tomographic redshift bins, which are used to measure the shear signal, and that can lead to a bias in the shear power spectra if not modeled correctly, as well as generating spurious fluctuations in galaxy density. Essentially, if there were no underlying large-scale structure, variable survey depth would create the appearance of large-scale structure. We can correct for that, but we can never correct for it perfectly. And so that's another example of an effect that we worry about and how it couples to other effects like blending. And then with the Rubin Sims team, we're working to develop observing strategies. These are these possible small changes in rolling that might improve things, that would have all the current benefits of rolling for time domain studies, but achieve better uniformity at these key data release intervals. So all the results shown, here's your big disclaimer in bold red. Our work's in progress. We've achieved a bunch, but the final outcomes are still under consideration. And so it's Eli's turn.
Yeah, so one of the big questions is, what is the impact on the uniformity of the photometric calibration? And so this, I started with Peter's, this is Lynn's old UberCal sim code, which was resurrected, and start with just the R band. And I have some a sample star catalog extending over the whole footprint. And in the year 1 of the baseline strategy, we have no rolling. We need to build up templates and everything. And this is in the upper right corner, a map of the photometric calibration offsets for some realization of, using these sample stars. It's very simple in terms of systematics, but I want to see the impact of the rolling. And it is uniform at the 5 to 6 millimag level, using very simple assumptions. In reality, we'll be able to do probably better than that. But in the lower right corner is, if you take the first year of rolling only, this is 18 to 30 months, worst case scenario. If you calibrate that on its own, then you see the stripes, because those parts are thin and they're offset and they're noisier. And I'm working on, quantifying this, but you can see by eye, the photometric uniformity is not good. Again, this is, don't start by doing 100% rolling, which we wouldn't anyway because of building up templates and all of that. So if we go to the next slide, just as an example, in the upper right corner is Y2 only. And this is 12 to 24 months, and it's a mix of rolling and non-rolling. And there are some offsets in the north because of just where the Northern Galactic Cap strategy happens to be. But overall, the metrics here are much better than the pure rolling. So the tentative findings so far, as long as the first 18 months pre-rolling goes as planned, if you calibrate together the rolling with the non-rolling at the initial baseline, then everything is actually well tied together. It gets tied together through that initial year plus of non-rolling observations. So the little asterisk is, if the first 18 months don't go as planned, then this will affect more than just photometric calibration. It'll affect the templates, but we want to make sure that we have that nice tied together baseline, and then we can roll, and the photometric uniformity, I think, will be fine going forward from there. That's it.
Okay, thanks, Eli. So the next two metrics
Rachel, since there is a switch, I see Bob has his hand raised.
Oh, yeah, of course.
Thanks, Rachel Fed. Eli, thanks. I'm just wondering, does the photometric calibration in this case include attempt to use Augstel at all? Or
This
is
is very
just
simple. This is not, the effect, the short answer is no. And this is a very simple UberCal, and it doesn't have all the chromatic systematics, and this is single band, but Augstel will have negligible impact at this level, because we have to understand the instrument very well before the atmosphere has as much an effect. But what the key point here is basically taking a ratio of, fundamentally a ratio of rolling and non-rolling, to make sure that our observing strategy is not messing us up. And if that makes any sense, the point is that we want to make sure that the rolling isn't messing us up. It does not mean that we are magically going to have easy photometric calibration uniformity. It just says that our job, the impact of the observing strategy is minimal, provided we start with a nice uniform baseline.
Thanks.
Okay, so the next two metrics that we're developing have to do with the impact of depth fluctuations across the survey footprint on the samples that we're using for cosmological weak lensing and galaxy clustering measurements. And so just to set the stage for that, before going to a science-driven metric, we wanted to develop a metric that just sort of at a technical level lets us easily quantify the magnitude of those depth fluctuations across the survey, those coherent patches with different depths that you saw in some of the previous maps, which produce essentially large scale power, like if you were to take the power spectrum of those. Okay, so to do that, we essentially computed power spectra of those maps and integrated the power on very large scales to get the total integrated power. Again, the idea here is to just have a crude way to quickly quantify the amount of structure in those maps. And so this plot shows an illustration of what that looks like as a function of the year, measured at 1 year increments for a few different strategies. So the dashed blue is especially one you should pay attention to because that's the baseline V3.3. There's a no roll V3.3, which does not roll at all. So that, again, that's not consistent with what the SFC has recommended, but it's kind of provided as like a best case scenario, right? Because the best case scenario is not a completely homogeneous survey. And then the other 3 lines show variance and rolling, which I'm not going to talk about too much right now. Matt Becker is going to tell you more about those later, but for now, just suffice it to say they are variance on the rolling cadence. And so you can see that at year 1, all of the strategies do the same thing because rolling hasn't begun yet. But then after that, they diverge at times, quite significantly. And that's a good way to quantify the structure in those maps, in terms of like a single number, essentially. Next slide. So one important source of systematics that can arise due to these depth variations is that when you use magnitudes, like a cut in magnitude, to select a sample to use for cosmological analysis, the mean redshift of the sample that your cut actually picks up will vary actually as the depth varies across the sky. And so in principle, if you knew that perfectly, you could potentially model and remove it. But if there's any residual that's difficult to model, then that could lead to biases in the observed cosmological measurements that we make, 2-point statistics, correlation functions and things like that, which we would model without knowing that there is this additional variation happening across the sky. And so what we've been doing is trying to, excuse me, to say if you pick a particular limiting magnitude for a sample, like what's the expected variation in mean redshift across the sky? And then we follow a paper that was recently published that shows essentially if you have that unmodeled variation, what does it do to the cosmological measurements that we're going to use to measure things like the growth of cosmic structure and dark energy. And so the right-hand plot shows biases in the measured power spectra due to that effect. And you can see it's for different strategies, again, including baseline, which is now red. And you can see that goes up quite a bit, for example, in year 3, which is strongly affected. It's still somewhat affected in year 4, which we think will be an important timeline for analysis. And so we've been using this essentially as the basis for a metric where we, again, we don't compare to no bias, we compare to what no roll is doing as sort of a best case. Next slide.
Okay, I think that's my turn. So Eric's already mentioned that we're interested in contamination or spurious modulations of the galaxy density. And that comes up in various applications, one of which would just be galaxy clustering, where you try and measure cosmological parameters directly from that, but it's not the only one. And what's interesting is that it's particularly affected by variations on the sky of the observing conditions, such as depth. And so we're developing various avenues to try and measure that, model that, and how we can also plan for the survey itself and account for the strategy, just try and predict what we're going to see. So the first figure there, the upper left, is one of those tests on the DC2 simulations where it's showing actually the contamination signal itself. So the red and blue is basically spurious fluctuations in galaxy density. And the figure on the right is actually a fit of that with templates of the observing conditions. And you can see it's capturing quite a lot of the large-scale fluctuations, which is something we expect to some extent. And the figure actually on the bottom left is actually showing a measure of that that process. So the blue line is the variance. It's actually fractional changes in the total variance. So it's closely related to the metric that was talked about by Rachel a second ago. So blue is if you don't do anything, and the x-axis is as you go deeper and deeper. And this matters because we, of course, want to go as deep as we can. And we, in fact, we'll push that as far as we can with a sample like that. And the orange line is now, if you subtract the fit based on the observing condition maps, the templates that you basically have. And you can see, you can remove quite a lot of it, but it's not zero. And there's seems to be this incompressible floor of 5 to 10%. I don't want you to get hooked too much on that number because that's very much a function of what specific metric and how you calculate the variance and you subtract noise and those kinds of things. But this is, what's important is that we expect there will be a floor, and we're developing new techniques to try and get to that. What's important for this discussion is that that subtraction that we're doing here, going from the blue line to the orange line, won't be perfect. So that's one thing that we'll try to account for. And this is why having a survey that's as uniform as we can is important for us. And also that model that was used in that going from the blue line to the orange line, we can use it to make predictions for the different observing strategies that are being tested. So that's something that we're investigating now. So the bottom line is that we're developing different avenues to try and not only model and remove this kind of contamination, but also plan for what we're going to do and also try and assess future plans for strategies. And I'm done.
Yeah, so building on the work on depth and galaxy density fluctuations, we're also interested in understanding the potential impact this could have on cosmological analysis. So something that we have done is we have devised a very simple approximation for relating any of these unmodeled observing strategy systematics that Boris was talking about with biases on sigma 8. And this is what is shown here on the plot on the left, basically showing it for two different observing strategies, baseline in blue and orange, and normal in orange, sorry, both of them for year 4. And what this plot is essentially telling us is the amount of tolerance that we have for these unmodeled observing strategy systematics if we want to live anywhere below the year 1 forecast for the sigma 8 uncertainties. So there's two soft conclusions from this particular work. The first one is that there seems to be a small difference between both the baseline and the normal, so the blue and the orange curves, hinting maybe at hinting maybe that this is more of an analysis issue in the cosmological front rather than an observing strategy issue, which would be great. And the second softer conclusion is that we might have a low tolerance level for unmodeled observing strategy systematics overall. As you can see from the plot, if we want to be below this horizontal dash line, we have to be at about 5% of unmodeled observing strategy systematics, which is quite stringent. But again, this particular work might change based on some of the ongoing progress that we're doing on this front.
Okay, I'm Matt Becker. I'm a staff member at Argonne. I'm also the Deputy Computing and Simulations Coordinator for the Dark Energy Science Collaboration. I'm going to tell you about some of our ideas on new strategies for the rolling cadence and how it could be adjusted to achieve magically uniform samples or as close as possible anyways at key years when the community, including the desk, might want to do analysis. I want to really credit Peter and Eric for helping me in producing simulations and discussing ideas on how to get this done. It's been really great to collaborate with them. So we've done a bunch of ongoing experiments. Not all of those results were reported here. And the basic idea is that when we're running a rolling cadence in the survey simulation, there are basically 2 seasons back to back where you swap which parts of the sky get enhanced cadence. And then so there's this cycle of sort of up and down. And then usually what the baseline 3.3 has is you just do basically 3 of those cycles in a row. And the core idea here is what happens if we put a season in between the first 2 cycles that looks a lot like year 1. And that is basically what we've been testing. We've been testing variants on that. So there are variants where you could put uniform seasons between all of the cycles. You could also try, instead of a full year of constant sort of uniform observing strategy, you could try a smaller interval like 6 months. We've been trying to implement that and test it as well. And so the plot here is basically showing you sort of where we are in these sort of have our cake and eat it too approach. And the sort of the bottom line is that if you put a uniform season in between the first and second rolling sequences, so that means you're delaying them by those other 2 by a year, you'll get a much more uniform year 4 data release than you would otherwise. And this is the key point at which we think that these rolling cadences will cause issues, potentially anyways, for static science. At later years, the overall depth of the survey is so much bigger that the fractional change due to extra rolling is smaller. And so that's what's shown on the right. The dashed line is this uniform comparison. The dotted line is baseline 3.3. You can see some details of how the actual scheduler works, and that there's actually 3 constant seasons at the start of the survey. That's the 18 months. And then you see the 3 sort of periods of up-down rolling cadences. And then you see this orange line and the blue line, which are these strategies where we put 1 constant season between the first and second rolling sequences. And so you get as much time rolling. It's just that some of the time is shifted later into the survey, and that increases the uniformity at year 4 substantially. So what's going on next is that we found this was much more effective in version 2.2 of the simulations. I've put a link to a notebook showing that plot at the bottom than in version 3. And so we're trying to get to the bottom of it, of why this changed. We already, Peter very kindly changed one item. So that's the blue to the orange, which is a lower footprint weight. And we'll also look at other things in the simulations to try and improve this. So this is the sort of top line, is that this is a way to modify the rolling cadence such that you get as much time rolling, but there's this special year at year 4 that'll be really nice for static science. Okay, so I'll wrap this up. So this is a subgroup that's within the SCOC, largely being staffed by desk at the moment, although there are contributors from other science collaborations. We've been trying to make progress on quantitative science-driven metrics. All of the results are work in progress. We have 3 new metrics that are going to be put into math in the near future to try and assess survey uniformity. And we're working out proposals for ways to shift some of the rolling around so that we can find key data releases where the data looks a lot more uniform. And that's everything.
Excellent. Rachel, do you have more slides?
No, I don't have more slides. We were just closing with this the update from this subgroup that's been working on this.
Thank you very much. I am going to ask Saurabh to proceed with his presentation on the DDF task force because both task force chairs actually have teaching commitments, and I want to make sure that he gets to the end of his presentations. But there will be time for questions for the people that have spoken in this slide regarding this slide deck and this topic right after Saurabh's presentation on the Deep Drilling Field Task Force.
Okay, thanks, Fed. Can you all hear me? Can you see the slides?
All good.
Okay, great. So this is one of the other task forces that Fed mentioned in her talk. This is the one, we're just sort of getting underway now. So this is just be an introduction. We won't have as many beautiful results as what you just saw. Okay, so this was shown again in Fed's intro. This was the phase 2 SCOC recommendations on the DDFs. And I won't read the whole thing, but note, up to between 5 and 7%, it recommended Euclid Deep Field South as the 5th field that's split in 2 pointings, as Lynn showed. The Cosmos field that's by itself would get 10 years of observations in 3 years and then continue to be observed. So those were the full recommendations. This is what it looks like on, I think Lynn showed this as well. These yellow dots are the deep drilling fields. And Lynn had a very nice slide, so I stole it. So thank you, Lynn. So I won't summarize everything she said just a little while ago, but here are the details about the deep drilling fields in the current baseline simulations. And just one thing to note is that each of the DDFs at a minimum 20K visits, well, I guess the Euclid, that's about 10K visits per pointing, all the way up to 40K visits for the Cosmos field. And just to keep in mind, that's compared to about 800 visits per pointing to the wide, fast, deep. So it's much, much deeper, much more time on these regions. It enables a whole range of additional science. That's the whole idea of doing this, and the idea of spending a significant chunk of survey time on the deep drilling fields. So the phase 2 recommendation next steps said that the SCOC will continue working in 2023. Okay, we're a little late for that, but with the community to identify intra-night cadence that maximizes the science throughput of the DDF survey. So basically, within the outlines of what was set before, in terms of here are the fields, Cosmos should be observed in the first 3 years to 10-year depth. The other ones should be observed relatively uniformly. Within that sort of cadence outline, what are the recommendations we can make about how the DDFs should be observed? And so that's the goal of this DDF task force, to provide a recommendation to the SCOC with quantitative assessments and based on metrics on the scientific impact of intranight cadence and choices. And I'll show some more specific questions in just a second. So the members of the task force, this has been being put together over the last few months. It's not a final list. If you would like to join, especially if you would like to work, we need people who can commit effort. That would be very welcome. So please let me or Fed know. So of course, the task force includes members of the SCOC, so they're listed there first. And then other members from the different science collaborations. I think all the science collaborations who have an interest in DDFs have suggested members to this task force. And of course, we need the help of Fed and Lynn and Peter, and you've already seen some slides about how they are looking at possible changes to how the DDFs get observed in the simulations. So the deliverables, we were tasked to make recommendations to the SCOC by the end of May. So it's a pretty intense period of work over the next few months to get questions figured out. And so what are the questions? So these are some of the questions from our charge. So exactly what filters and how many on a given night per DDF? What are the sequences, meaning what are the number of exposures in each filter? How are filter sequences and fields reprioritized for weather and downtime? Do you just stick with a fixed schedule, or do you go back if you've missed certain filters, et cetera? The cadence has generally been suggested by the phase 2 recommendations, but exactly how that works, for example, how the Cosmos field will get observed in the first 3 years to 10-year depth, there's still some details in the implementation that we can make recommendations about. Are there limits? So for example, if the sky is too bright, the moon phase is too high, or the transparency is low, should we just not do DDF observations during those nights? So what kind of constraints might we put on the observations? And then a key thing is for all of these SCOC recommendations, it's there's the scientific output but it's based on metrics. And so the question is, do we have the right metrics? And then do we have the right simulations of DDF observations to answer these questions? So a lot of the beginning of our work will be focused on checking all the DDF related metrics, make sure we have all of them, and then suggesting the right simulations to do to make our recommendations. And I think that's all I had. Sorry, oops. Okay, I'm not even going to start the presentation again, but I'm happy to take questions as we get started. And as I said, expressions of interest in working with the task force. If you're interested, please let me or Fed know, and we'd be happy to have you. Thanks.
Emphasis on working. Thank you for highlighting that, Saurabh. Excellent. Questions for the presenters in this session, or comments that are arising from the questions as well. Bob.
Thanks, Rob. This is really cool stuff. To remind folks, we still are in contact, of course, with our Euclid colleagues about the Euclid Deep Field South, and as everyone knows, Euclid's off and running now and taking data. They will continue to, and they may even have some data in the Euclid Deep Field South already. I'm not sure. They will continue to take data in that deep field for some time over the 6 years of the baseline survey. And there will become a time where the schedule of those observations is known. It may already be known. We've been talking to our Euclid colleagues about that last week at the AAS, and we'll continue to. But at some point, we may come to the SCOC and to Lynn's team and say, hey, we now know what the Euclid schedule is. How can we look at optimizing to the extent that we have, the ability to, going forward, coordinated observations in that deep field, because that might be very interesting, obviously, to have simultaneous or near simultaneous data. And I'm just throwing that out there as a kind of a heads up that question that will almost certainly come at some point, and then for this group and for Lynn's team to start thinking about how that might torque or otherwise not torque cadence aspects.
Yeah, that's a great point. I mean, it's something that has come up, coordinated observations specifically for that field. Yeah, so as Fed had mentioned, the SCOC will continue to exist throughout operations, but it's an interesting point about, if you do want to concentrate Rubin observations of that particular field at a certain time, how does that affect other things?
Thank you. Actually, I'm going to take Neil's question first, Knut, if you don't mind, because I think it's for the DDF.
Okay, thanks. Yeah. Thank you for all the work on this already. I'm representing, of course, the AGN science collaboration, and I suspect this point is broadly relevant for some of the other ones as well. So the AGN science collaboration has worked pretty hard to develop some good, thoroughly considered ideas about the deep drilling field cadence. These have been provided as a white paper, as a cadence note, as other inputs to folks working on cadence issues. But unfortunately, just due to limited funding, we have not been able to express these as formal metrics. And so how do you plan to ensure that those inputs will be properly considered in planning the deep drilling fields? I think this is quite important, just given the practical realities of the situation.
Well, as a member of the task force, how will you ensure that they are included? I guess I can turn back to you. No, I think it's a good point. And, one thing that we should, if there are proxy metrics that can help, if you say, oh, this particular metric, if, it can be interpreted in this way for AGN. And so we're going to, it may not be obvious that, that metric is so important, but if you can show that it is, for what you want to do, that might be a good way of saying, we need to pay specific attention to this one metric, maybe out of a list of 10 or 12, it wouldn't have stood out. But, if you say, oh, that's quite important for AGN, that's definitely the kind of information that's useful.
Okay. Forgive me, I wasn't aware that I was a member of the task force. Did,
Yeah,
did
you
I
were.
volunteer at some point, or have I been volunteered? without a-
You were invited to a Slack channel recently, and yeah, so please check Slack.
Okay,
Yeah,
thanks.
we received information that you were on the task force, but we can talk about it separately. But let me add that this I think is a point that is worth emphasizing for all the activities of the SCOC. I think over time we've translated the vast majority of science cases into some sort of metrics, some more really true to the meaning of the science case, some very much a proxy for the science case, yet some of course remain uncoded because of limited person power. The SCOC, the survey strategy team, has supported the community and continues to support the community to turn science concepts into metric. We had suggested a math tutorial in this workshop, and we got a fair amount of requests for doing it, but we decided to actually devote a little bit more time and a little bit more concentration to it separately. So as Lynn will indicate later, we'll share it. There's already tutorials available. We will share another video tutorial with updates, and the survey strategy team is available with office hours. So part of the responsibility of the task force is to identify what critically needs to be turned into a coded metric for the success of the task force, and we can work together to actually make that happen. But thank you for bringing it up, Neil.
Thanks a lot. Thank you.
And of course, like not everything needs to be a metric, right? So some experts and domain experts can identify critical points, even if there isn't a coded metrics, and we do listen to that input as well. And with that, Knut, I want to give you the microphone.
Thanks. Yeah, this is a question. So I brought it up in chat, but maybe I could expand a bit as for the uniformity task force presentation. So that was really great stuff. From Federico's slide, I think the conclusion that I saw was that whatever observing strategy one chooses, one has to model the effect of the observing systematics in order to to achieve the results that desk wants to achieve, and that you had to do that no matter what the observing strategy is. And at least in the plot, it didn't look like there was much difference between the no roll and the rolling cadences. So I mean, I appreciate that if the SCOC can make simple, win-win choices to increase uniformity of the survey, that's good. But how hard should the SCOC be working to ensure uniformity, particularly if there's trade-off between having a uniform or a cadence that gives you uniformity versus one that might, for instance, benefit time domain applications? If you have to do the observing strategy modeling anyway, and you're confident in your ability to do it, how hard should the SCOC be working to try to ensure uniformity?
Matthew, go ahead. You're the right person to answer this.
Yeah, so I want to mention just like a few points. So first, I just want to reiterate Eric's big, warning that all of these results are preliminary. I don't know if, we all in the desk fully believe that conclusion yet. That is the conclusion you would draw from that plot, but this is all work in progress. And the second thing I'll mention, and I posted in the Slack, is that this is true for galaxy overdensity, which is a big deal. May not be true for other aspects of the analysis, like the mean redshift variations or things like that. So you have to be careful in how these conclusions are phrased. And then I can't speak for what the SCOC should or shouldn't do, but I will say that the degree, how hard it is to actually make these corrections. One, like nobody really knows how to do it at LSST depths. And that's always going to be true. That shouldn't be used, in my opinion, as an excuse to make the survey way less uniform or way more uniform. But I think there are reasonable compromise solutions that delay the arrival of some of the time domain, but will hopefully make lives easier for a lot of people on the static side. And I'd really like to see us exploring those as a way to provide everybody with a little bit of what they desire out of the survey.
Matthew, certainly, and that's, that was one of the responsibilities of the task force, right? It would be really important for the SCOC to understand if there is a critical degree of inuniformity that prevents the analysis, or some critical points at which the calibration and the correction of the systematics becomes, increases significantly, and perhaps increases non-linearly with the lack of uniformity, because that will give us, concrete goals to strive to, and concrete impact to measure against the impact that changing the rolling might have on time domain science. And I know that this is what you're working towards, but just to clarify that. Any other questions? We are 3 minutes past the beginning of the break. Let me double check the schedule to see that I'm correct and that break is next. Yes, we can officially enter our break, and we'll see you in 27 minutes. Sorry for eating 3 minutes out of the break. At that point, we will talk about in detail about the throughput updates and the updates to the OpSim and the science, the impact that they have on the science metrics that we're monitoring. So please come back in just less than half an hour. When we come back, please, the SCOC, remind me to restart recording so I don't forget, and I also don't have to record 30 minutes of silence. Thank you for the reminders to record. We are recording again, and I think we're ready to start with the next session. So, Lynn, take it away.
Okay, it says my screen sharing is paused. I don't know if that's...
Yeah.
That's okay.
But it is, hold on, let me make sure that, I only see a little bit of it. It looks like it's zoomed in a lot, unless I'm doing something wrong.
It looks fine for me.
Okay.
I think that's in Zoom. You can scale your
gotten stuck.
view, so you might be zoomed.
Lynn, it's fine. I think.
Okay.
Go ahead.
I maybe needed to switch my screen. Okay. So this is session 3. We're going to talk about what those system throughput updates were, and then how that leads into the question of what metrics we have and potentially missing metrics. So in V3.3, the baseline, I said we switched to this new system throughput update. We now have as measured throughput curves for the broadband lens coatings in the camera, the mirror reflectivities, and the filter throughputs. We also have measured QE curves for each amp, but we don't use those for the purposes of the OpSim simulations. We just use an average for the full focal plane. The big change here is a change from aluminum, silver, aluminum to triple silver mirror coatings. So you see here in this plot, the dashed lines are the 1.7 throughput curves. So these are the throughput curves we used in all V1 through V3.2 simulations. They were not based on as measured values. The 1.8, there is a version of throughput, so this 1.8, but which is as measured, but with this different coding. What we're looking at using is the 1.9. Sorry, Doug wants to go out. Of course. 1.9. That's the solid line in these throughput curves, which is triple silver mirror coatings, and this is the current expected performance. Okay, so what you notice there is that the throughput is increased in GRI ZY bands and is decreased in U band. And if you look at like sort of the offsets, we're talking about, 0.1 to 0.2 magnitude increases in 5 sigma depth in GRI ZY, and then about since it's really in some ways we're comparing to 1.7 because those are the old simulations, but in another way you might say we're actually should be comparing to 1.8, which is just the other alternative for the throughput curve. So depending on exactly how you count it, it's we definitely have a noticeable drop in depth for U-band. However, if you look at what the actual those throughput the 5 sigma depths are, they do meet the design required depth in all bands except R band. And so R band is actually improving relative to the SRD with these triple silver mirrors. And it exceeds the minimum requirements in all bands. So R band gets closer to design depth with triple silver, and the overall survey efficiency improves by about 20%. And that's because even though we have less depth in U-band, we have fewer U-band visits in the survey than in any other bands. So improving the efficiency in GRIZY ends up to be a net win, even with this loss in U-band. And you can look at this 20% increase in survey efficiency as an opportunity for retuning the survey strategy to get more science. So this may include using some of the essentially freed up time to, it's not technically, we're still using the whole time of the survey, but you could say, well, we're going deeper in these other visits, so we can reshuffle some of the time. So we could add visits or extend exposures in U-band as one of the options. So the SCOC is starting to look at how do we evaluate the survey strategy, relatively small tweaks now on this, and you should follow updates on community.lsst.org. The V3.3 baseline uses the same survey strategy, but with these new throughputs. So that's the thing to remember. And there were those very small effects that I talked about earlier as well. Okay, so this is the major change in 3.3. We can look at the effect on the metrics. So some of these plots, you maybe have seen them before. These are what we call the radar plots. It's a way to sort of maybe see an overview of a bunch of metrics at once. What you see here, the blue line is the V3.2 metric results. So those are sort of the normalized values. And then the orange lines are the V3.3 metric results. And outward on the radar is a better metric value. These are just a subset of metrics. Again, like we always end up showing a subset of metrics. And you've maybe seen these same metrics in the mesh grid plot, but here I just put them as a radar plot so you can get some at least some measurement of the increase in what the value is. So basically, these are static science metrics on the left. Things like the number of stars, number of galaxies, parallax, proper motion, and those have all improved or stayed neutral. And on the right, these are transient based metrics or transient variables. And in the metrics which we show here, these are all increased as well or stayed neutral. If you look at the visits per pointing per filter, that's my little plot up here. This is not a ratio plot. This is a actual change in the number of visits per filter per pointing. And here you see V3.2 and 3.3. I think I showed this earlier, and you can just see the number of visits overall in U-band increased per pointing slightly, again, because of that bug that we fixed, so that U-band is continually being acquired. And then the number of visits in the other filters is, there's a very small shift, but it's basically the same. Okay, so in general, our metrics improve. Most of these metrics, when you look at what they actually care about, are being driven by the increase is being driven by the increase in those GRIZY depths, because the number of visits is about the same, but those individual visits are a little bit deeper. The SRD metrics improve. So here, this is the SRD number. This is the median number of visits per pointing in the wide, fast, deep is basically what this translates to. And you can see all the way through from V1 to 3.3. And this is relatively neutral because, again, we don't get that many more visits per pointing, but you see that the uncertainty in proper motion and the uncertainty in parallax have decreased. These note that up is better, and these are smaller numbers, larger numbers. These are in milliarc seconds. So this is the this SRD metric about the proper motion uncertainty for faint stars, and this is the parallax uncertainty for faint stars. And because of that improved signal to noise in GRI bands, that's what's driving these improvements. There were some other metrics that I thought might care about U-band depth in individual images, but it turns out they don't, because they either have improved or they stayed relatively neutral with. And here we're showing the uncertainties again. Remember, I talked a little bit about those weather variation runs and how we use those to set some uncertainty. And that's what these error bars are coming from, is the standard deviation of these metrics across that set of weather runs. So supernova 1A discovery is improved because it doesn't actually care about the depth in U-band so much as the signal to noise in those GRI ZY bands. The same thing with the kilonova detection metric. And then the this is a metric that looks at, like, can we detect anomalies and identify them as anomalous? And that stays relatively neutral. And then one that I really thought would care about the U-band individual image depth was the total number of detected TDEs, tidal disruption events. And oops, sorry. And this one, because I thought this one might in particular because it requires a U-band color. So it requires a color as well as a U-band visit. But we had slightly more U-band visits. And so that is, together with the increased depth in the other bands, is probably what's driving this increase here. So these were all metrics that I thought would maybe care about the U-band depth, but didn't. There are some metrics which do decrease with U-band depth. So there's, for example, there's one solar system metric which looks at, can we get a color in every band, including U-band? That one obviously falls because the solar system objects are faint in U-band, and then we're making the detection limit worse in U-band, so that falls. But that's not their highest priority metric. So I just pulled out some metrics which we know are high priority that do decrease with U-band. One of these being the total number of stars detected in U-band. So the plot here, let me explain this for a second. So this is the total number of stars in U-band across all the simulations. The gray line is the number of stars that were detected without including any effects of crowding. And then the black dots are the same thing, but including the effects of crowding, and saying we're going to stop measuring when the precision hits 0.2 magnitudes of uncertainty due to crowding. And that stays much flatter. So I think this is important to look at, but the effects of crowding may actually mitigate that decrease in U-band depth quite a bit for stars. The total number of galaxies detected in U-band also falls. That's this blue line here on the plot. But the number in R and I band and GR and I band increase, and in Z band and Y band also had a slight increase. So